Good afternoon, everyone. After a long day of talks, hopefully you are still awake. Yes, so yes, I'm representing here today a large team constituting of researchers from both VTT and Aalto University, and in this Finnsores project called Biooptics, where we are developing fiber optics from forests. And well, I am working at VTT. Fiber optics. Well, we live in a digital age today. All of you probably have a cell phone on you, probably a laptop. We transmit enormous amount of data every day. We receive and transmit. For short distance applications, wireless, yes. But actually for long distance application, what transmits this enormous amount of data around the world? And the answer is fiber optic cables. They are the real workhorses of data transmission on our planet. They connect continents from other continents, and actually they are the backbone of the modern digital age that we live in, apart from the electronics. Now, what are optical fibers? They are essentially glass fibers, very simply. So, very simple architecture. There is a glass core. There is a glass cladding, which has a little bit lower refractive index than the core. And essentially, what happens is what is shown in this very simple cartoon, that the light bounces off the interface of the core and the cladding, so undergoing so-called total internal reflection, and then keeps going on. State-of-the-art glass optical fibers are virtually lossless. So they lose about 0.2 decibel of data per kilometer of transmission, and it's a result of continuous improvement over decades. Fiber optics were invented in the 1960s, and the state of the art today is a result of very, very fascinating innovations in how to purify the glass and how to remove all the intrinsic losses from the material. Of course, plastics have also made their way into this domain. There are plastic optical fibers used mainly for short-range applications. They are not as lossless as glass. Now, fiber optics are not only used for telecommunications and transporting data, they are actually widely used in sensing. They have several benefits. They are small size, lightweight, robust. They are very, very sensitive to even very small stimuli. And they are actually immune to electromagnetic interference, which makes them very interesting in applications where you cannot use any medical parts, metal parts. For example, in medical applications, it would be an MRI machine where you cannot have any metal parts when you're going into the machine. So you need to have sensors that are immune to EMI. And that's why fiber optics can, in that application, play a big role, and they actually already do. Variety of sensors, environmental sensing, chemical, all kind of movement sensing, all kind of gyroscopic sensing as well, strain and current as well. But the largest domain here lies in the environment and the chemical sensing part. Now, how does cellulose play a role here? So cellulose in optical materials, well, it can be in the form factor of not only fibers, but also films. Cellulose films, well, I think most of you are aware, good strength, thermally stable, much more stable than plastics, at least the soft ones, biocompatible, non-toxic, and of course you can modify them. And good thing is that you can also have very transparent and very non-hazy materials made out of cellulose, and you can tune that. You can have translucent materials, you can have hazy materials, and there are many, many possibilities to tune the optical properties. And as I said that, of course, you can functionalize cellulose, so it changes a lot in terms of the properties of the material itself. It also changes a very important parameter which governs the optical properties, and especially in the case of fiber optics, and that is the refractive index. So you can go from, as you can see, as we change the functionalization on the cellulose backbone, we can change the refractive index. And even though the change is not very big, it is sufficient. So for context, the difference between the refractive index from the core and the cladding of optical fiber can be as low as 0.05 refractive index units. So you can actually essentially realize a cellulose optical fiber just from different cellulose derivatives. And if we see how to actually prepare these fibers, the method of choice remains wet spinning in the literature. You can make these fibers either via the regeneration approach, so to say, where you dissolve the cellulose in a solvent, then you wet spin it, regenerate, remove the solvent, dry, and you get a fiber. Or you can use the so-called hydrogel approach, where you don't use any other solvent, but you actually use water as the solvent. You make a hydrogel, you spin a filament of that hydrogel, and then you immobilize and dry it as such. And this is suitable, for example, for water-soluble derivatives of cellulose. So if we look into the literature, this is a slide where I say that I am very proud of the first optical fibers made from cellulose were invented or reported for the first time at VTT in this work in 2020, where we use a regenerated cellulose fiber core, and we make coaxial spinning, and then we have a cellulose acetate coating on the fiber, and it comes out looking like picture on the top right. And this was the first reported optical fiber, and this has opened the floodgates, so to say. There has been following work from Germany, and also, of course, we still, this Finseres community between VTT and Aalto, we still remain the pioneers of this topic. And we have now shown optical fibers made not only from regenerated cellulose, but also of other derivatives with methyl cellulose, carboxymethyl cellulose, and so on. Now, typical properties of cellulose optical fibers, how do they actually work in carrying data from point A to point B? So here's a picture of a loop made from methyl cellulose optical fibers, spun with a very simple method. You dissolve the material in water, then you spin it in an anti-solvent and immobilize and then dry. So the transmission window, so to say, of the cellulose fibers, it remains in the visible and the near infrared region, starting from 550 to about 1,400 nanometer. And if we actually look at the typical telecommunication wavelengths, so they lie also in the infrared. Glass is actually very good material to transport near infrared light, about 1,300 nanometer. And the attenuation, so basically the data loss of these fibers is between 1 to 6 decibel per centimeter, which depends on what kind of fiber raw material you choose and what kind of process you choose to make those fibers. But again, these fibers are able to transmit light in wavelengths that is relevant for use. Now, certain applications. So in this case, we don't want to compete with glass fibers. They are so advanced in doing what they do that it's a little bit silly to compete with them in long distance data transmission. Where we want to go into is short distance application and actually sensing. And cellulose, well, it loves water, and why not start with something which interacts with cellulose very well? So one example here shown is water sampling, where we basically dip the fiber loop into water. It could be any other mixture of any other fluid into water as well, and then we can actually see how the transmission through the fiber changes with time as the fiber wets. And this is reversible. You can dry the fiber, use it again. So it's kind of a sampling device. We can extend this to colorimetric sampling. In this application, we use a very simple test where we take a red food color, put it in water, dip the fiber loop in, and take the transmission signal through the fiber. And as the water moves and the dye as well moves into the fiber bulk, we can see that if we are looking at the red wavelengths, so we can see that the signal changes in those wavelengths. So this is one way to measure and also quantify certain compounds in water or any other liquid just by using a very simple portable system where you can sample with for example, a pen type tool. Very simple application again is touch sensing. Of course, when we use bare fibers, if you touch the fiber, light leaks. You can see that in the signal. So in this case, every time the signal drops, that signifies touch.